All right, this is the Chapter 3 review for the semester exam. So let's get started working through these problems. And in number 1, it's multi-part answer, of course. So we're going to evaluate this function for these given inputs. So for letter A, when we do f of 2, we do 2 squared minus 4 over 2 squared. And the numerator, of course, is 0 divided by 4. So the answer for 1A is 0. All right, for number B, f of negative 2, we do negative 2 squared minus 4 over negative 2 squared. And this is 4 minus 4, which is 0, over 4. And the answer there, again, is going to be 0. Letter C, f of negative x. So we do negative x squared minus 4 over negative x squared. And we simplify, and that is x squared minus 4 over x squared. And it's a good habit to get into to factor when you can. That will open up opportunities to cancel potentially. In this case, it doesn't, but you'll be able to catch those opportunities when they arise. All right, and then letter D, the opposite of f of x is basically taking, we need to take f of x and multiply it by negative 1. And so that's just basically making this entire fraction become negative. So there's your answer for letter D. And then for letter E, we're doing x minus 2 quantity squared minus 4 over x minus 2 quantity squared. When I square this binomial in the numerator, it's x squared minus 4x plus 4 minus 4. And then this is x squared minus 4x plus 4. So when you simplify, you get x squared minus 4x, and then the 4 minus 4 becomes 0. And then this is x squared minus 4x plus 4. I'm going to go ahead and factor and just see if anything cancels, x and then x minus 4. And then in the denominator, it's x. Let's see, that does not factor. So as it turns out, we weren't able to cancel anything. So that ends up being our answer for the f of x minus 2. Go back and circle these answers. All right, and now let's take a look at number 2. So going back to letter E, this denominator does factor, but it doesn't allow us to cancel anything. I just caught that. So we could call this x minus 2 squared, but that doesn't help us. Just want to make sure you don't lose points when you could factor and cancel. If you don't factor, then you won't know for sure if you can cancel. So just trying to help you out, catch every point that is possible. All right, so for number 2, letter A, the f of 2 is the square root of 2 squared minus 4, which is the square root of 0, which is 0. Letter B is the square root of negative 2 squared minus 4, and that's going to give us the same result. That's 4 minus 4 square root of 0, which is 0. Letter C, f of negative x. So we put negative x in place of x, and that's going to be the square root of x squared minus 4. For letter D, we're just going to do, this is like multiplying -1 times the original function, and that just gives us the opposite of the square root of x squared minus 4. And then finally for letter E, we input x minus 2, square it, and then subtract 4. So squaring the binomial, x squared minus 4x plus 4 minus 4, and that gives us x squared minus 4x under the radical. So the square root of x squared minus 4x. All right, moving on to number 3. This is operations with functions. So given these two functions, we'll do the f plus g. So that's literally just adding these two together, combining like terms. 2x plus 2x is 4x, and -1 plus 1 is 0. So the f plus g operation would give us 4x. And now we'll do the f minus g. And got to be careful with subtraction because it can be tricky. So if you use the distributive property with -1 on the second binomial, that's helpful. So -1 times 2x, -1 times 1, and that gives us 2x minus 2x, which is 0. -1 minus 1 is -2. So there's the answer to f minus g of x. For the f times g, we're going to do FOIL. 2x minus 1 times 2x plus 1. So 4x squared minus 2x plus 2x minus 2x makes 0. And then subtract 1. So there's the f times g of x. And then we'll do the f divided by g of x. And that's taking the f function, dividing by the g. Can't factor either, so we can't cancel. Please don't cancel terms. You cannot cancel terms, only factors. And now let's go back and we'll do this second sentence. For all of these that end up as linear, this would be like the y equals 4x, that's linear. A constant like -2, this is quadratic. The domain for all of these graphs is all real numbers. Okay, it's only when you have a fraction like this that you have to be worried about restricting the domain. And so we cannot allow an input for x to create 0 in the denominator. So if you're not sure, then take the denominator, set it equal to 0, and solve for x. And so we cannot, the domain is going to be really all the numbers except for -1/2. So really we could call that a domain restriction because there's really only one number that needs to be left out of the domain. Okay, so now let's work on number 4. Same thing, f and g added together. This is where we have to get a common denominator, and it's going to be x times x minus 3. And we divide x minus 3 into the common denominator, gives us x, and x times 1 is x. Here we divide and the x's cancel, so we're going to multiply 3 times x minus 3 to give us this new numerator. That's 3x minus 9. And now we can add these together, and that would be 4x minus 9. But we have a couple of domain restrictions. X can't be 0, and x can't be 3. All right, so there's the addition answer. And now we'll do the subtraction. It's really going to basically be this same setup here, except we're going to be subtracting, of course. And again, you need to be careful with subtraction because you're subtracting both of these. So x minus 3x is negative 2x. And then when you subtract negative 9, that's really adding 9 all over x times x minus 3. And can't do any factoring and canceling. So that is our result for the subtraction part, and we have the same domain restriction. X can't be 0, and x also can't be 3. All right, and now we're going to do the f times g. So 1 over x minus 3 times 3 over x, and we just multiply fractions. So 1 times 3 is 3. Over x times x minus 3, and that's our result for the multiplication. And then we have those same two domain restrictions. X can't be 0 and x can't be 3. And then finally we do the division. And you could start off thinking like this, but dividing by a fraction means to multiply by its reciprocal. And so instead of thinking this, let's just go ahead and flip the denominator and multiply. So 1 times x is x over 3 times x minus 3. And we only have one domain restriction here. X cannot be 3. All right, so looking at our graph, this is number 5. The domain and range of this function. For both, it's going to be all real numbers. Where is f increasing? Well, it's increasing on this interval. I'll just kind of mark on the graph. It's increasing until we get to x is negative 2, and it's also increasing here. So we'll say that increasing from negative infinity to negative 2, and it's not actually increasing at negative 2, so you don't want to bracket that. And then it's also increasing from positive 2 to positive infinity. And it's decreasing in this other interval. Let's make this black. So this is showing a decrease, and that decrease is occurring on the interval from negative 2 to positive 2. And again, at those actual points, it's like stable. It's not increasing or decreasing, so don't want to use brackets there. The local minimum, and that's just another way. We used to, in Algebra 2, we use the word relative, and they mean the same thing. But these are turning points. So we have a local minimum here where it's making a valley, and we'll say it's at x equals 2. The value of that is the y. The value of that minimum is negative 1. And then we have a local maximum at x equals negative 2. And the value of that is positive 1. Okay, absolute maximums and minimums, in this case we don't have them because this graph is going to go forever. It's never going to stop going up, and it's never going to stop going down. So to have an absolute, you would have to have a point like this where it stops and it doesn't go on any further. That would represent an absolute maximum, or same thing for minimum. But in this case it doesn't have either, since it never stops up or down. And then finally, do we have symmetry with respect to the x-axis, the y-axis? If you had symmetry with respect to the x-axis, you should be able to fold on the x-axis, and the top half and the bottom half should meet across the fold. That doesn't happen. If you have symmetry with the y-axis, same thing. You should be able to fold your graph on the y-axis, and the two sides of the y-axis should meet over the fold. We do, however, have symmetry with respect to the origin, and the way you could see that algebraically is, I'll just take the point 4, 3. If you have ordered pairs that match in number, but the signs are opposite, then that's an indication that you've got origin symmetry, like -2, 1, and then you notice you have 2, -1. Same numbers, but the signs are completely opposite. So that's an indication of origin symmetry. And if it has origin symmetry, then it's considered to be an odd function. If it were y-axis symmetry, it would be even. If it's neither one of those, then obviously it's neither. So you either have origin symmetry, that would be odd, y-axis would be even, and those are your two options. All right, so now let's do algebraically determining whether these functions are even, odd, or neither. So the test is we're going to input -x in place of the two x's. And we want to see, after doing that, do we end up with the original function? Well, it's pretty, when we input -x and we do -x to the third, we're going to get -x to the third. And then when we do the multiplication here, we get plus 4x. Well, that's completely opposite of what we had originally. And so notice, kind of like what we talked about over above when we did the origin symmetry, the two coordinates in the ordered pair had opposite signs. Well, that's what's happened here. And so this is going to be odd. Okay. Here, when we put the -x in place of x, and we do same thing on the bottom, when we square both of these, we're going to get positives because they're even exponents. We end up with the same exact function, so that means this has to be even. And then here, when we do f of -x, when we raise -x to the third power, we get -x to the third, and that's not the same thing as what we had originally, so this is going to be neither. All right, number 9, the average rate of change is another way of saying the slope. And slope in ordered pair form, we use the formula y2 minus y1 over x2 minus x1. When we're doing functions like this, it's f of x2 minus f of x1 over x2 minus x1. Okay, so I'm going to do f of 3 minus f of 2 over 3 minus 2. All right, so f of 3 is 3 squared is 9 times 2 is 18 plus 7 is 25 minus f of 2. 2 squared is 4 times 2 is 8 plus 7 is 15 all over 1. And so the average rate of change is 10 units. All right, let's get the graph of number 10. This would be the graph of, just think of y equals 3x, that linear function that would have a y-intercept of 0 and a slope of 3. All right, I'll just do several points. But according to this restricts how much of that line we're actually going to draw. It's going to really create a segment. And we want this to only exist between the x-coordinates -2. So I've really not gone far enough. I've gone to where we have an x-coordinate -1. And now I've gone to x-coordinate -2. And over here, I stop when I come to an x-coordinate of +1 on that line. So I've got a point really that I don't need. And so this is going to be our segment. I need to make a little adjustment. At -2, that should be open. Let me make that a little clearer because it doesn't have or equal to. And it'll be closed at +1. And then I'll do my best to draw a straight line segment. Okay, so there's the graph of the first piece. And then this is another partial, well, it's going to actually be a ray. It starts at 1 and then has a slope of +1. All right, and then we only want this to exist, though, for all x's that are greater than 1. Okay, so not including 1. So right here, I'm going to make this open. And then we're just going to show a ray going in that direction. This is the direction where the x's are greater than 1. So don't really need that red dot right there. All right, so there's the graph, and then we're supposed to do domain and range. So the domain is going to be all x's that basically start here at -2, not including -2, and they're just going to go forever to the right. Since we have a disjointed couple of segments here, but the 1, even though it's not included in the red, it would be included with the black. So all x's that are greater than -2, and not including -2 since that's open. And then for the range, we start here at 1, 2, 3, 4, 5, -6, and it's just going to continue to go upward because of that red. There's a little bit of overlap, and it's just going to continue to go up from -6, not including -6. So there's the range. Is it continuous? It is not. It's pretty obvious that at x equals 1, we have discontinuity. To be continuous, you should be able to just start on the left end of the graph and go all the way across to the right end forever, as long as it goes, without ever having to pick up your pencil. Obviously, that's not possible because we'd have to pick up our pencil to get from the black piece to the red piece. So there's your answer for number 10. And there was one other part up there, letter C, that I just noticed. We're supposed to locate any intercepts, and we do have an intercept here at the origin. All right, let's take a look at number 11. The graph, just think of this as y equals x. So y equals x does this. If we did the whole line, these are some of the points. But we're just going to do a segment, and it's going to be the segment between x is -4. Haven't gone quite there yet. So here's -2, here's -3, and here's -4, and it will be solid at -4. And then we're going to stop on that line where x is 0, and it's going to be open at 0. And this is our segment. It's not real straight or nice. Okay, and then y equals 1. Okay, so that's a horizontal line, but it's only for x equals 0, so that's really just describing the point 0, 1, which is right there. And now we'll do, just change the color up a little bit, we'll do y equals 3x. So that also starts here at the origin and has a slope of 3. Okay, and it doesn't include the origin. So it's kind of like I've got another open circle here. Red and black are both open. And it's going that way forever. Okay, domain. Well, let's see. The domain starts at 1, 2, 3, x is negative 4. And it's going to continue to go to the right, it looks like, except we have this open circle. However, the open circle, you can kind of think of it as being closed by this red dot. And you can also see, as part of our description of the three pieces, we're told that x equals 0 in one of the pieces. So 0 has to be part of the domain. So anyway, starting at, what is that, 1, 2, 3, negative 4, and we're going to positive infinity. It's just going to keep on going to the right. For the range, let's take a look at, we're starting at 1, 2, 3, 4, negative 4. For the range, we just have a little interruption here. Since the circle at the origin is open, that means we do not have 0 as part of the range. So we'll break this up into two intervals. We'll go from negative 4 to 0, not including 0. We do include negative 4, because that's a closed circle. And then we're going to combine that with 0 to positive infinity. So basically we're just jumping over 0 as we proceed upward from negative 4. It is not continuous. And it looks like we only have one intercept, and that's this red dot that sits on the y-axis. So that would be 0, 1. Right, let's move on to 12 and 13. What are these parents? And you should know all of them at this point. So this is the cube root parent, number 12. Number 13, of course, is the quadratic parent. So again, I gave you a little note here. Make sure you know all of the library of parent functions. Make sure you can transform parents. So here we have the absolute value parent, and it has been shifted 1 to the right and 4 down. So I'm going to go x minus 1, 1 to the right, 4 down, minus 4. Notice that it's kind of tricky. You got to be careful here, because the parent has a slope of positive 1, which would do this. But this slope is positive 2, up to right 1, up to left 1. So that's called vertical stretch. So that's why we're going to have to put a 2 in front of the absolute value. This is the quadratic parent, and it has been shifted 1, 2 to the right, and 3 up, and it's also been reflected, and so we'll put a minus in front to show that it's a reflection on the x-axis. Right, and then finally we have dilations, and this is the quadratic parent, and because it's being multiplied by a number greater than 1 in the front, this is called vertical stretch. When you multiply like in this of course is the absolute value parent. When you multiply by a fraction between 0 and 1, this is called in front of the function, I should say, in front of the absolute value. This is called vertical compression. Okay, as soon as we move numbers on the inside, that automatically makes these horizontal effects. So both of these are going to be horizontal. Outside is vertical. Okay, so you can see the parent. So where it was vertical compression on the outside, it becomes horizontal stretch when it's moved to the inside. And where we had vertical stretch when the number was on the outside, the whole number, when we move it to the inside, it becomes horizontal compression. If you think about it, vertical stretch makes skinny. It takes the regular parent and makes it skinny. And so does horizontal compression. That means we're pushing, basically think of pushing from the sides horizontally. And it obtains the same type of effect. Okay. And that's also true. Horizontal stretch. Vertical compression is another word for squish. It's going to broaden or widen the, in this case, it would be the V shape. And if you think about it, taking the two sides of the V and pulling on them would be like the stretch move. That would create the same effect. All right, I think that's it. That takes care of your Chapter 3 material that you need to be prepared for the exam. And if you need any other help, if you have any other questions, let me know.